Hi everyone, my name is Lydia and this is what I wish they had taught me about econometrics and introduction. In the previous video, we talked extensively about the differences between mechanical and statistical properties, so in this video, we'll continue to go in deeper about mechanical properties of the OLS. There will be 5 mechanical properties that we are going to talk about, but in this first part video, we're going to only see the first 3 ones and go over the proofs for each and every one of them. You will see very easily how they all come from the first order conditions that we set in the minimization problem of the OLS. The first mechanical property is that the sum of the OLS residuals is 0. Mathematically, we will write these as the sum of the residuals is equal to 0. The second mechanical property is that the OLS residuals are uncorrelated with the explanatory variable sample values. Mathematically, we are going to write it as the sum of xi times residual being equal to 0. The third mechanical property is that the OLS regression line cuts through the means, and the way that we will write these mathematically is that y bar is equal to beta null hat plus beta 1 hat x bar. So these are the first 3 mechanical properties that you will have to remember. The other 2 mechanical properties, we will see them more in depth in another video. So let's see the proofs of each and every one of the first 3 properties. As a reminder, we've seen in a previous video the algebra behind the OLS. We've started from the minimization problem which was the minimization of the sum of the residual square and the residual, using our information about the fact that the residual is the difference between what I observe and what I estimate. We rewrote it as the difference of yi with the actual line that we would be estimating. A reminder, we wrote them down as B0 and B1 as an indication that right now we don't know yet which is the best candidate. We just know there are a few candidates and we're gonna do the algebra to get to that candidate. How do we solve it? Like any other minimization or maximization problem, we do the first order conditions, and the first one with respect to the beta null gave us this expression that we see right here. Now, remember, we said that the fitted value is literally beta null plus beta 1 hat xi, which means that this entire expression in here is actually your y hat. Then you are left with an expression that gives you the sum of yi minus y hat equal to 0. But again, we know that the difference between yi and y hat, it's your residual. So that means we can just write it as the sum of your residuals being equal to 0. And that would conclude the proof of your first mechanical property. So as you can see, it's directly implied from the first order condition. When we did the first order condition, it was because the end result of the algebra was to get the beta null hat. From there, we got that the beta null hat was y bar minus beta 1 hat minus times x bar. If we rearrange this expression, we can write y bar equal to beta null hat plus beta 1 hat x bar. Okay? So as you can see, it means we're using the means for the y bar here and the means for the x bar in here, which means we have technically just proved mechanical property 3 in here. So this was mechanical property 1. So through the first order condition with respect to the beta null, we have actually proved 2 of the 5 mechanical properties. Now let's go back to the second first order condition, which was with respect to beta 1. So the expression that we got was that the sum of xi times this big bracket equal to 0. Well, now, from the previous first order condition, we know very well that this is just the residual. So it means that if I rewrite this expression, I have simply the sum of xi times epsilon hat I, the residual, equal to 0. And that concludes also the proof for your second mechanical property. So you see, it's very easy and straightforward. And these will always be true no matter what the data that you have. To show you that, I have prepared a little worked example in here, and I'll walk you through it. I've just taken a small data set, 4 data points. I have done a few computations already to make this video go a little bit faster. But keep in mind, you've got data given in here, x and y. The I in here is just to indicate to you that this is my first observation, second, third, and fourth observation. If we use the formulas that we already have for the beta, or the procedure that I have shown you on how to get the betas manually in a previous video, you will find that the beta null hat in here is going to be 0.8, and the beta 1 hat is going to be 0.8, and you will find that the beta null is going to be 2.5, which means that your OLS fitted line is going to look something like y hat I equals to 2.5 plus 0.8 xi. Okay? Based on this fitted line, we can now compute the fitted values in this column, which I have done for you. And then based on the fact that now I have information on both what I observe and what I predict, I can easily find my residual. Now that I have the values for all of my residuals in this column, I can continue to do the computations and to check all the properties one by one. So checking properties. From the first one, we can see the sum of the residuals. Very clearly, we've got minus 0.3 plus 0.9 minus 0.9 plus 0.3, which cancels everything out, and we will get finally a 0. So we have checked the first mechanical property here, very clearly satisfied. Let's check the second property, which was that the sum of xi times the residual is going to give me 0. So in here, I will have 1 times minus 0.3 plus 2 times 0.9 plus 3 times minus 0.9 plus 4 times 0.3. You can do the computation very quickly, but I've already done that for you. And as you can see, you can express everything as a factor of the 0.3, and you'll see very clearly that they will cancel each other out. So this will end up being also a 0. And we have this way checked the second mechanical property, that the residual is uncorrelated with your x values. The last one, the line passes through the means. We can very easily compute here that the x bar is going to be 2.5 and the y bar is going to be 4.5. From here, we can evaluate the following. So we know also we can evaluate the average of the y hat as well, which will turn to be a 4.5. You can do it directly through the table, but you can also say, well, I know that my y hat, right, is going to be 2.5 plus 0.8 times the 2.5, which we found for the x bar. Doing the computation is going to give you a 4.5, which is, again, exactly the mean of your y, okay? And that has proved you that basically the line passes through the means. I hope this was helpful for you to understand the first 3 mechanical properties. We still have 2 more mechanical properties that we can prove, And so I'll see you in the next video.